to make sure the recording.
Yes, I am. Thank you.
Sure, go ahead.
Yep. All right. Good morning, everyone. I'm Luke Miller, PhD student. So today's talk is in a quantum physics lecture. I'm not going to actually touch a single quantum algorithm. Okay, I'm looking at more of a high level of why quantum. Okay, and everyone in here is at least passingly familiar with AI. Okay, and my central thesis is quantum computing and AI are driving to solve the same kind of solution. What do you do when the search space is too big when you need to find an exact answer? Okay. AI is approaching this through the lens of heuristics, trying to find good answers. Quantum computing is approaching this from the space of efficiency, of how can we better explore the space? And how can we solve this problem more quickly? Both are responses to the same problem. The number of possibilities that we have to check is much larger than the capabilities we have. Now, that could be things like, this would take until the heat death of the universe to compute. Or this could be things of like, no, we don't have time to compute this. Okay, hey, if I'm trying to make a decision on the best portfolio for me to invest in, it's kind of useless. It takes me a year to calculate that based on the data I had when I started. Okay, so there's things like that we're bound in two directions, both in the tractability on how long does it take to find a persistent answer, and these time-bound answers where, okay, this answer is useless in the time it takes us to calculate. All right. So this is the basic overview of my talk, okay? The computational space that we have access to, we've made amazing gains in what we can do with multiple cores on a chip, computational power, data centers, what we can approximate with AI or heuristic solutions. But anyone familiar with scientific and engineering fields knows that you don't have to go far until you find a problem that's intractable in computation. Okay, there's more chessboard configurations than atoms in the universe. Now, we have some great AI solvers for those. But at the same time, it's infeasible to do a deterministic all possible pairs comparison. Okay. And so that's one of those things where this is where quantum is emerging on better being able to search those spaces. Okay, for some scales of problem, we may be able to fully search the space. For other scales of problem, this may be married with AI, where we're using quantum computing to do a better search of the space by marrying the two together. Hey, we're using quantum computation to represent the space, to do constrained optimization on the space, and pairing that with AI in its heuristic search. And that's the central theorem is that AI is great, okay, but it's not the ultimate good. There's not a single problem that we could use AI for if we could deterministically calculate in a tractable amount of time. Okay, me passing an image to a computer vision model and doing all this math and guessing that it's a cat, if I had something that could deterministically tell me this is a cat, or even more importantly, there's an obstruction in the roadway, or there's a tumor present in this, we do that deterministically instead of doing this rules-based search and guess. We absolutely would, but we can't. That's why we use AI. And that's also what motivates the use of quantum computing. You know, this quantum computing may reduce that computational burden for selected problems. And I'm going to keep saying this for like selected structured problems. Quantum computing is not some universal accelerator. There are classes of problems that it has advantage. I'll be careful with using that word, but has potential advantage with solving. Okay, it's classes of problems that it doesn't. All right, it kind of comes down to the right tool for the job. Okay, in my kitchen, I have a microwave and an oven. Okay, if I need to reheat a cup of tea, I'm likely going to use a microwave. If I need to bake a cake, microwave is probably the less good choice. And also, it's not quantum or AI. It's not quantum or classical. It's not the merging of them. Okay, we're going to use quantum with quantum's best at. We're going to use classical with classical's best at. We're going to use AI for the things it's best at, things like representation and heuristic search. Okay, these are all going to bring stances for this hybrid instantiation. Okay. Additionally, I want to kind of ground it. I hear a lot of people err on both sides of the quantum problem. Okay, there's some people who's like, oh, it's too noisy, it's taking us too long to figure out algorithms. There's no proof that it can, solve this class of problems. I think that's too dismissive. And there's some people who are like, it's going to solve everything tomorrow. Okay, which is also, the wrong stance to take. It has problems with the noise and coherence, the hardware. Okay, but we do seem to be rapidly addressing them. There's no clear ceiling on this. On like, oh, we can tell that like we're going to hit this wall in 2 years. There's no clear wall that we hit in 2 years. There's engineering problems, there's logic and software problems, there's algorithm development that hasn't been done yet, but that's not the same as saying there's some fundamental ceiling to what we can accomplish. All right, so this isn't a methods lecture. Okay, so if you came here hoping to hear about Shor's algorithm or variational quantum eigensolvers and stuff, sorry. I could direct you to some great resources that I've put on YouTube in the past or something. Follow up with me after. But this is talking about the overall landscape of like, why is quantum important? Why should we take quantum seriously and like what are its limitations? So it's all about these computational limits. Okay, we have these difficult computational spaces. That's where AI emerged. If you read, some history of computation, the first AI approaches were these expert systems people trying to develop. If X then Y, if Y then Z, if Z then A. From there, we progressed to some things like, basic linear regression. We have things like the early genetic algorithms. And then we started, in the early 2000s, getting into neural networks and backpropagation. Okay, but all of these are trying to solve this problem. What do you do when space is too big to search? Quantum computing manages this though, because it can reduce that computational burden for some of these problems. Okay, and I want to be clear here. I'm not saying it instantly solves these problems. All right, it reduces computational burden. You may be able to better search the space using some quantum algorithms. I'm going to have an example later where I'm showing how this applies in practice. Okay, so it's not AI versus quantum, but what happens with AI plus quantum? All right, there are different responses to the same pressure, but with different fundamental approaches. So there's two big approaches to this problem's too big. Okay, there's more compute and there's more efficient compute. Okay, and these aren't in opposition. They obviously should go hand in hand. Okay, and AI is approaching both of these problems hand in hand. Okay, we are scaling up these data centers. All right, cloud compute is bigger than ever. Big data is bigger than ever. Okay, simultaneously, real research is going into making these transformers or large language models more efficient with the compute they use. Quantum computing is another approach to try to make better use of compute time. So, with scale, it's more compute, more data, more memory, more infrastructure, better connectivity. Okay, and efficiency is about better algorithms, better representations, better search, better computational regimes. And so like, an example of this that comes to mind is, so with you're using a vision model, you can pass it the raw image and just try to let it work it out all the way into end. But we're relatively good at that for the scale of images you probably take on your phone. Okay, with some freshmen and things, but it becomes more difficult whenever you're talking about like gigapixel medical images. Aerial photography with thin structures like power lines. And welding is this huge thing with like trying to image to find cracks and stuff in welds. It's really difficult for computer vision as it exists today. So then the question becomes like, oh, well, can we get a better representation? Is the raw image that's nice for us the best representation for computation? Could we convert this to some compressed format, maybe in terms of a graph, something like that? How can we do this more efficiently while still achieving our aims? All right. So it's not better computational structure. Okay, it's not more compute, it's the marriage of the two. Okay, whenever you're talking about scaling up, you're talking about an inherently linear process. Okay, so I mean, usually you're talking about this scalar thing, all right? I can multiply times 2, times 3, times 4, with the data centers will build, but it's really hard to make those jumps from a linear problem to a quadratic problem to an exponential problem, where we're not talking about a difference in a multiplier. We're talking about a difference in what, complexity the machinery we're talking about. And that's one of those things where we're not equipped to address that by just expanding data or memory or infrastructure. So it requires both approaches. This is why AI took the form it did. I mentioned this in my introduction a little bit, but if we could use an exact method in a timely manner, we would. Okay? AI is a stopgap to an inability to process the space precisely. Okay, so AI emerged as a, frankly, quite elegant solution to like, okay, we can't search the entire space. What's a smart way we can do that? Whether that's gradient descent or, whatever the case, whatever AI method you're talking about. Okay, you can't search the entire space for the optimal answer. Is there a way that we can approximate a good one? That's why AI emerged. We're talking about these computational spaces that are too large to approach. Okay, and so with these, we can learn these representations that become practical substitutes for the exact analytical structure of the data that we're talking about. Okay, we're no longer operating on the real data. We're operating on a representation of it at a abstract level. So this approximation, optimization, adaptive search is what modern ML is. Okay, and that's whether that's a simple model you're running on your laptop or training the biggest large language model out there. We're trying to optimize a landscape that's too big to search. So they're useful when the exact structure is too expensive, too brittle, or infeasible to search. So, there's kind of this hierarchy of how we apply AI. Okay, we use exact rules when we can. If I can, I don't need AI to tell me the answer to, 23 times 10. Okay, that's practical. I can solve that, from a human perspective instant. Okay, so whenever that becomes, inexact, then we start talking about hand-designed features. Now, this might be a thing of compressing an image. Okay, hey, I can hand design this feature where I compress this image or maybe apply a specific kernel, and I'm able to get a compressed representation of this that I can then do my computation on. Then there's the learned representations where instead of me hand designing how we're going to compress this, I try to let a neural network or some other AI model make a compressed representation of the space so I can do search on it. And then there's this adaptive search. Now, there's not clean lines where this model fits here, this model fits here. Okay, most modern AI models are using a combination of all of these. Okay, they're trying to do an exact search on what is the actual gradient at this position. There's hand-designed features that we're applying to it with whatever we're passing in, feature engineering, cleaning your data set, things like that. It's learning a representation of that space, and it's doing an adaptive search over that space with whatever optimizer or whatever the thing is that the model is using to make its updates on what its predictions are. So AI is this limits of computation story. And that's what we're going for with quantum computing. It's like, how can we reduce these limits of computation? And it's easy to forget we've made amazing advancements in computing. All right, the things that we can do now would shock someone 20 years ago. At the same time, you don't have to go far until you run into a problem that's difficult to calculate. Okay? If I give you 100 binary choices, flip these 100 switches. Okay? If you're just talking about the combination of those switches, you're talking about 1.27 times 10 to the 30. Okay? If I say the order you put the switches in matters, you're talking about on the order of 10 to the 157. Completely intractable. I don't care what device you have, you can't do an exact search on that space. Even at the scale of the heuristic search on that combinatorial space becomes inaccessible. All right, this is why we have these heuristic searches where we're like, okay, we're going to try these switches, that didn't work out very good. We'll try these other switches, that kind of worked good. We'll try variations on those switches. So that's where we use AI for these reasons, because you don't have to search far with, combinations of things before you run into these problems. And it's like, if I took 10 of you and I was sitting you in chairs, I have over 3 million choices of how to position 10 people in those chairs. So whenever you go from 10 people to 20 people to 30 people, it's not multiplication. You're starting to deal with this level of math. And then it's one of those things where we kind of ignore it because everyone, I think, whenever they started to learn the code, or the first time they started playing with it, wrote a program that would have taken until the universe expires to run. And you realize, like, oh, I can't do that. And these workspaces aren't exotic. Okay, I'm not creating these fabricated examples using some clever math, come up with a place where we can't compute something. Okay, anybody trying to solve an optimization problem in science or engineering runs into this time and time again. Okay, like graph matching and substructure search. All right, so a graph is just a network. You have a collection of nodes and the edges between them or the connections between them. Okay, we've managed to enumerate all graphs up to 14 nodes. Okay, beyond that, it's just intractable in memory and computation to enumerate how many graphs there are. 14 nodes right now is kind of the ceiling the limit. So like that shows you just how close that is, all right? So trying to enumerate, the possible structures that exist, you can see that you clearly want bigger than 14. Scheduling and routing, Amazon, the United States Postal Service drop millions of dollars a year in research and development on how to route their vehicles. Okay, these graph traversal problems or these navigation problems, scheduling problems are real. They have a real economic impact, and people want these solutions to them. Molecular discovery behavior, whether that's folding or how it interacts with those sites, this falls into that same camp where it goes, it goes vertical as far as complexity. Feature selection and model search. This is the thing where I'm talking about quantum and AI working together, where if I have 15 parameters I can tune on a model, I'm now easily talking about billions of possible configurations if those are discrete binary choices. Usually they're continuous. So it's just a completely inaccessible search space. So intractability in this sense isn't rare. It's not some like niche application where like, oh, well, in this specific domain, you can construct a mathematical problem to make your argument. We run into it constantly in every field. All right. Now, efficiency has several meanings. Okay, and I'm sure a lot of people, when I say efficiency, are like speed. Speed. But there's a lot of different kinds of efficiency here. Okay, there is speed, which is a good thing, but there's also like how much actual compute do you use? If it's if I run my problem on a supercomputer, is that more efficient? And it depends on your means, but maybe, maybe not. All right. There's also data efficiency. How much data do you need to make a prediction? It's how much actual information do you get from your compute? Okay, I can design an algorithm that completes, nearly instantaneously, but gives me no reasonable information to work off, so there's everything from that to a perfect answer. And also just with aligning the computation with the problem structure. All right, every time that someone writes a program, they're taking this real world idea and trying to put it in this computational language with these representations. How well are those things aligned? Okay, does my simple little graph really capture the dynamics of a potential drug? Maybe. How many details do I need to encode? The bond strength, the electronegativity, the exact molecules, chirality, whether it's twisted left or twisted right. So it's one of those things where we're often making this huge trade-off between what the real world object is that we're trying to solve, whether that's scheduling, the portfolio that we're trying to optimize, and what we're actually using. So there's efficiency in that scale. How well are we actually representing this thing? So whenever I'm talking about efficiency, I'm talking about contrast between the effort and resources committed and the quality of the answer we're getting back. All right, I'm going to transition into quantum now. We talked about the size of search spaces, why AI is developed to combat these search spaces, but I kind of want to make some quick disclaimers on what quantum is not claiming. We do not make all of our problems easy. There's a specific subset of classes that typically have strong relational features that we capture with entanglement, okay, and have these very large search space type problems. Okay, if it's a very linear processing thing, you're likely not going to use a quantum computer to capture that. Okay, if you need to do a series of math problems where one answer feeds into the next one, most likely you want to use classical computers. A quantum computer is probably going to give you less precise answers at greater cost. There's a specific subset of problems that quantum computing is good for. Quantum computers will not replace classical computers, and that ties into what I was just saying. All right, that's in 10 years, we're all not going to have a quantum computer sitting on our desktop. Okay, because there's no reason to. 99% of what most consumers do is captured well by your classical computer. Current noisy hardware already gives broad advantage. IBM likes to use the term utility because advantage is a mathematical point. Advantage is this is better than any possible classical algorithm. Okay, we're not claiming that. It's been proven for a small subset of problems, often at scales that aren't achievable on hardware today. However, we have demonstrated utility, and that is the quantum computer gave us a better answer or an answer competitive while being efficient that we haven't matched with classical computing yet. So that's where IBM's made that distinction between utility and advantage. Advantage is this mathematical claim beats any known classical algorithm. Utility is this claim that's kind of where the rubber meets the road. Of like, no, we're getting real answers to this. We're getting better answers with this. We're getting faster answers with this right now. Maybe someone could one day create a classical algorithm that competes with it. And then superposition means brute force parallel search. A lot of times that's how this is framed, and I understand why. We try to relate this to people who haven't delved into quantum yet. At the same time, you are able to use superposition to explore a wide search space in parallel, but it's not the same as testing every possible combination and getting an exact result. All right. Just as a brief example, don't worry too much about the semantics of this, but there's a quantum Fourier transform. Fourier transform, we decompose a signal into a constituent set of waves. Okay, it does not line up every possible combination of these waves, creates a probability space for the constituents of it that you're able to then use to do your calculations. So it's not the question of a universal speedup, it's problem to structure fit. Okay, there are some problems that quantum computing seems like it might be a good fit for. There's a lot of problems that it is not. And it's all the time because people know I'm into quantum computing. So it comes up and he's like, hey, I have this thing. Well, quantum computing is good for it. Can we talk about your search space? What is it you're trying to optimize? Are you hoping you just add quantum on top of your method and get faster? Probably not. So it needs to be suited to that space. There needs to typically be some kind of intractability element going on here. That, hey, we are having to apply rough heuristics to do it. We're barely scratching the search space that we're trying to. So way we can use quantum to make better use of that space or to search in a more efficient manner. So what quantum could add? All right, richer computational objects. So with quantum space, for every input space, you would get an output that's 2 to the n on that. That's both a blessing and a curse. It's a very rich space for exploring and to extract information from. That I take 20 inputs and I create a 2 to the 20 output space over those bit strings. And that's where that problem structure fit comes in. Is that like it provides a richer computational object for us to work with. Okay, and we use a similar concept in AI all the time. All right, with the kernel trick going from higher dimensional objects down to lower dimensional objects and back and forth. Superposition and interference and the quantum thing. All right, instead of focusing on perhaps the physical interpretation of how and why these things work, I think of them as computational resources. I can use entanglement to propagate this information between these entities. Okay, I can use interference to help me select the best option in this optimization space. All right, it's not naive brute force, but structured exploration of this complex space. And it has a lot of applications. All right, there's optimization. There's the reason it was proposed in the first place. Okay, the reason someone first thought of a quantum computer was that, like, hey, if we're going to calculate what quantum objects are doing, we probably need a quantum computer. All right, sampling in that hard combinatorial structure. All right, as a little aside, all my work always centers around graph theory. That's my main focus. All right, I might use graph neural networks for image processing. I might solve a graph problem with quantum computing. I might have some other graph domain AI. It all comes back to graph theory for me. And that's why quantum computing was attracted to me in the first place. Okay, where we're getting into these combinatorics of how do these things combine, how do these things commute. So here's the bottom line with that. If scalable fault-tolerant systems are achieved, which we're not there yet. Okay, the systems we have right now are noisy. There's a limit on the coherence time that we have to extract a useful thing out. But there's not a clear ceiling that we seem to be progressing towards this. We're solving the engineering problems associated with getting scalable fault-tolerant systems. So if those are achieved, some problems now treated heuristically might become accessible to exact or certifiable methods. Okay, we're changing the tractability of the search space. Okay, and that's going to take place in two primary forms. There's some things that we're going to be able to move out of heuristics and into determinism. We can solve this problem with this level of certainty. Okay, and then there's the things that are going to be still intractable for complete search with quantum computers. Okay, quantum computers don't provide an infinite speed up on any class of problem. But what we'll be able to achieve then is a better search of that larger space. In that scalable fault-tolerant systems, I just submitted a paper and I'm characterizing this graph embedding using a quantum circuit. And as I'm characterizing its error and its noise and all this and stuff, I ended up hitting a wall. Whenever my circuit had a depth, like it was 250 operations deep, I stopped getting usable information out. There's that limit. Now that's just with the current hardware. 5 years ago, someone would have been amazed to have a circuit that's 250 gates deep, running up to like 66 qubits. But all the same and stuff like that, they're like, hey, that's the wall of what I have. I was able to recover things with some like error mitigation and stuff like that. There's still that wall where like, hey, my circuit can only run so long until the whole thing just becomes noise. Not getting useful answers out of it anymore. But at the same time, we're moving that direction. Deeper circuits, wider circuits, better results, lower error rates. So I want to tie this to a little bit more specific of a problem. So if we're trying to take a look at a graph and understand what effect its neighbors have on it, and tying this back to the real world, we could be talking about epidemiology. How does disease spread? And you could have a social network graph, the people you've interacted with and stuff, and how strong of an effect does that have? Now, right now, for these large problems, a lot of times we're doing local propagation. All right, we check at step, 1 step away from you, 2 steps away from you. So like your friends, friends of friends, friends of friends of friends. But once we start getting to like 3 hops, friends of friends of friends, okay, that's kind of Not a hard limit. There's people out there trying to do bigger things and stuff like that. There's kind of a limit for most large graph neural networks. Okay, it's hard to go much further than 3 hops. All right, what quantum offers is the chance through that entanglement to propagate the global structure to a node. Okay, where if for my graph, if I have this representation of what's likely to spread, what's the strength of the connection between these things, I'm able to propagate all at once to you how everyone you're connected with and they're connected with is propagating towards you. Okay, now there's trade-offs here. Sometimes this local information is very necessary. I need to know how your 1 hop neighbors are contributing to you, your 2 hop neighbors contributing to you. Whereas this, I'm getting the global structure all at once. There's trade-offs, okay? One provides a higher fidelity impact of the entire structure contribution to this factor. All right, and one's giving you a more granular level analysis, but it's just limited by the computation. So quantum is good for the search problem, but also the representation problem. How does the network affect everything as a whole? How do we represent this data? And how do we learn from it? So this local refinement, proceeds in stages. Check 1 hop neighbors, add the 2 hop neighbors, in larger receptive fields, approximate graph level structure. We use this method to do graph embeddings, but it's still a very inexact thing. Consider these approximations, and you can be solved with similar, or you can be fooled with similar looking graphs that it's hard to differentiate. So this local structure is handled effectively. We understand, out to a couple hops, what the network looks like from your perspective. Whether you're a server and who's connecting to you and who's connecting to them, we can get to a couple hops. But it's very hard to characterize what's the effect of the global structure and how that affects this particular node. And so that's what that graph embedding I was working on this last month was capturing. So using a quantum circuit to create a graph embedding that's characterizing the entire structure of the graph in one element. That's resistant to permutation. It doesn't matter how you order the nodes, you get the same output, and it's representing the entire structure of the graph at once. And so that's the trade-off that we're saying, is that sometimes we need to know what the global structure is. All right, some domains where this is especially important, protein folding, drug discovery, even cybersecurity elements, where you can have these long chains of function calls or connections and things like that, where checking 1 or 2 or 3 hops just isn't sufficient to understand what's really happening here. It's really easy for me to list together 30 function calls that call one another and to understand what this is doing and how it's affecting the global properties can be complex. And so that's what I was trying to do there. So that global embedding, where we're saying, what does the entire network look like from the perspective of this node? Or what is the properties of this entire graph, is what allows us to get that graph level output distribution. So it's not simply performing a local neighborhood check, but it's taking a look at the entirety of the thing all at once. So it's time for the synthesis. Why quantum and AI together? Quantum needs AI, and AI needs quantum. All right. AI is good at representation. It's good at pattern extraction, generalization, and that adaptive search. Quantum is good for that structured exploration of the space. It's good at constrained optimization, simulation, especially of quantum objects, and sampling and dealing with those high-dimensional combinatorial structures. All right. Hybrid doesn't mean replacement. It doesn't mean do quantum then AI or do AI then quantum. It means merging them at every layer. You're going to have, for these complex problems, AI and quantum interleaved at every level of the process. All right. So a specific example is that quantum computers are ran by classical computers. All right. You have classical computers that are telling it to do the pulses, doing all that. Okay, so you need high performance and fidelity there. So you need high performance computing. But whenever I write a quantum program, I create this abstract object. We call it quantum circuit, but I'm not like soldering things together. Okay, it's just a way of saying what my program is doing. The problem is just like, you can have a classical circuit where you have an AND gate and a NAND gate and NOR and an XOR. Okay, but then your real hardware doesn't use those. All right, your real hardware has these constraints. Oh, wait, our byte size or, our memory location size is this, the size of our cache is this. There's all these extra constraints that come in with translating that circuit that you designed abstraction to do what you want into the real hardware. Quantum computing has that same problem. When I have my program with the actual, okay, and the programming language I use, Qiskit, I have access to like 40 or 50 different gating operators, but any quantum computer I usually use has 5. Okay. Not only that, whenever we entangle qubits on this, a qubit on a quantum computer is an actual location. Okay, and if I want to entangle them, I have to get them next to each other. So I have to do a whole series of swaps to do that, get all of these next to each other. Okay, and they're not all directly tied to each other. Like I have to move them around on this 2D surface to get them next to each other. Okay, and the series of moves I do there can have a big impact on whether my quantum algorithm works or doesn't. Now, that earlier example, I said I had that 250 qubit gate limit. All right, but once I got to 250 gates, my program stopped working. So too many swap operations or bad initial layout just means my algorithm doesn't return a useful result. So then we start getting into, okay, how do we plan this? Now, for some problems, you can just manually lay it out. Okay, hey, I've got a linear string of things I need to represent. Everybody just needs to connect to its nearest neighbor. Easy. I just plot that out exactly on my quantum hardware. Hey, put these qubits together. They can all pop to each other, entangle and do all the stuff that we need to do. But like for a lot of these network problems where we have this complex graph, there's no way for me to put every qubit next to everybody needs to communicate to. So I have all these swaps and things. And that's where AI helps quantum. Okay, this translation search of that, like, we have a problem here is that like, oh, this would be a great problem for us to solve with a quantum computer. So we need a quantum computer to plan the layout to put the thing on our quantum computer. Okay, and this is where we use AI and quantum in tandem, all right? The translation, which is what that process of converting from my logical idea to the real hardware is called, okay? That translation, we use AI for to try to do an adaptive search of the space for the lowest cost instantiation of my logical circuit. And it goes in the other direction too, where I can use this AI to make richer representations of the search space that AI can then use. All right. And if somebody comes to me sometimes, they're like, oh yeah, I'd like to do hybrid quantum and AI. Like, okay, do you want to do quantum first? Do you want to do quantum in the middle? Do you want to do quantum at the end? Do you want quantum everywhere? Like, so it's like, there's a lot of choices we make here on how they interleave. But like, that's where we're going to get the biggest results. A lot of the leading quantum algorithms are this hybrid architecture. Okay, we tune the parameters on a quantum circuit. Okay, how much should we rotate each qubit? How strongly should we entangle these 2 qubits? We optimize that using AI. Okay, so hey, we run the circuit, we get a result back. We change the parameters, we run the circuit, we get a result back. We'll use AI to optimize these results as we go, to find that optimal configuration of those parameters on how much do you rotate, how much do you entangle. And this is where I'm going to kind of start getting into like where we're at today. Okay, a few years ago we were playing with toy problems. Oh, look at this. If we scale this up one day, we might actually start doing real work. We're past that now. We're solving real problems with quantum computing. Okay, Moderna last year was using a quantum classical hybrid workflow. All right, they're solving these mRNA folding problems, up to 80 sequence long. They're projected to push that further and further. 80 was kind of where they reached their depth limit. They have it ready to go for 250. They're expecting ours to hit it. I'm pretty sure that was published in Nature. Certified randomness on trapped ion hardware. For everyone, afraid of quantum breaking cryptography, quantum also has the possibility to save cryptography, truly random numbers on this trapped ion hardware. Error correction and logical performance milestones. So what I mean by this is there's a couple of problems that quantum computing is facing right now. All right, one is error correction. All right, classical computers do error correction already. A lot of times they do it by a simple voting method. Hey, I'm going to multiply my data times 3, and I'm going to send it off. Whenever it shows up, I'll have it vote. Okay, for bit 1, you say it's 1, you say it's 1, you say it's 0, we're going to say it's 1. You know, we have a probability for a bit flip and stuff, so let's say that like, okay, hey, you have 1 bit flip, it's most probably still 1. You know, an error correction on quantum gets more complex than that, but we're working on these algorithms to recover that information that's lost through the noise that happens in quantum computing. You know, and like logical performance, we're increasing the coherence time, we're increasing the number of qubits we can get, we're increasing error mitigation and error correction techniques as we move along. We're getting better translation to where we can make these circuits shorter that they can actually fit on modern hardware. Last summer I did a big survey on quantum graph neural networks, like where it's being applied and stuff. And I had 30 pages. I wrote 120 because of all the applications out there where people are showing utility. Now, not advantage. I'm not saying it's solving everything better than a classical computer can. Okay, but utility is like, hey, we're getting high quality results in a timely manner from quantum computers. Okay, the people most interested in it right now is probably falls in 3 classes. There's people interested in the simulation problem. Okay, material scientists, quantum physics researchers, chemistry, those aspects. All right. Then there's kind of the medicine, and by this I mostly mean like drug discovery, protein folding type things. Okay, that's that representational space that's really hard to do well on classical computing. On all of the factors that are affecting how this molecule folds and how they combine, how this drug interacts with the receptor site. Okay, and the third is finance. Finance is very, very excited about quantum computing. Okay, because that portfolio optimization, how do I maximize my return given all these assets, is an incredibly difficult problem to solve. Okay, I could have 1 share of this, I could have 1 share of everything in the market. I can have 2 shares of this and 1 share of everything in the market like this. You know, it's whenever you're talking about 10,000 entities, it's a number that I don't even really know how to represent in a coherent way. You know, it's going to be some multiplier times 10 to the 1,000 or something, you know. There's a completely ridiculous number. So it's not necessarily that broad quantum advantage exists. Okay, we have some algorithms that employ things have quantum advantage, like Shor's algorithm type stuff, for research. Okay, they're interesting, and they're going to be especially interesting if the hardware catches up. But this utility argument is what's interesting, is that like we're getting high quality output and reasonable timescales using quantum computers. All right, and everyone likes to talk about how many qubits. All right, that's always constant. How many qubits? How many qubits? How many qubits? How many qubits? Okay, there's a lot of people who are pointing to the field and like, oh, they're stalling out. Okay, IBM, has been around in the range of 120 to 160 qubits for the last 5 years, but it's largely because IBM's focused on different methods. Okay, we talked about coherence, the connectivity between the qubits. IBM's newest computers that they just put online went from some qubits being connected to 2 neighbors and some being connected to 3 to all of them being connected to 4 neighbors. Okay, that likely halves my circuit depth for any problem that I did. Okay, so it takes my circuit that maybe would take runs at 400 and just gives me noise on current hardware and makes it work. There's the software and the translation. Okay, we're not only solving the engineering problems with the hardware, we're solving problems with the logic. We're creating new algorithms both for what problems we can solve with quantum and how best to run quantum, run the hardware, run the translation. And so it's one of those things that this field isn't progressing along one axis. Yes, we're trying to increase the error rates that we're getting. We're trying to increase error correction. We're trying to increase translation. We're trying to increase the number of qubits. There's a lot of axes that the quantum computing field as a whole is advancing on all at once. All right, so this is like where I want to circle back to what serious skepticism should look like. John Preskill, is kind of one of the leaders in quantum information theory and quantum computation. He's been talking about this stuff for 20, 30 years now. I do like his kind of balanced approach to it. All right, he's dedicated his life to studying this, but I'm just going to read this quote aloud. I know you all can read. But we should be realistic about the timescale for quantum computing having a big practical impact. All right, and we should appreciate that quantum computers probably won't be able to speed up everything we want to do with computers, but will apply to a special class of problems. And we still only have a partial understanding of what those problems are. Okay, and that's the thing of like, someone asked me, like, can I apply quantum computing to speed up my work? You know, I'm like, maybe. And that's because it's not only the limits of my knowledge, but it's the limit of the field's knowledge of how do we translate problems into a quantum domain. So there's a lot of questions to ask with quantum. There's several different schools of quantum hardware. We have neutral atoms, we have trapped ions, we have superconducting qubits. They all have their different strengths and weaknesses. Some have longer coherence, some have more qubits. You know, there's a lot of variation there. So what hardware modalities will scale for which class of problems? Okay. Which algorithms that we've tested on these toy models actually survive to real world instances? What are the actual engineering bottlenecks? I've seen no evidence that there's a ceiling here. Like, oh, once we reach 250 superconducting qubits, like we won't be able to go further than that. There's no evidence of any kind of like hard ceiling like that. But that's not to say that one won't emerge. You know, and what evidence to change our mind. So like what I want everyone to know, like my strong take here is like technical immaturity, not the same as technical impossibility. We're solving engineering problems and there's no clear wall to be advanced like this. All right, and I've already talked about this a lot with the execution stack, not being, it's still heuristic. We have to translate our logical idea to the real hardware. You know, and we're using AI to help solve that. You know, and it's crazy to think that the future of AI is just bigger models, more data sets. That's part of it. Okay, you know, these large transformers and stuff like that, it solve problems we thought were impossible 10 years ago. Okay, that's part of it, but like we need to look at the efficiency aspect as well, where quantum computing can merge with these to help us solve those problems. So AI is a solution to a search space being too large to possibly tackle in our strengths. Quantum computing is perhaps an answer to some of these limits. It's not universal, it's not the solution to every problem, but it may be a way to compress or get a reasonable answer in a faster time frame. I think the field is still young, okay, but we have the advantage of all the other computation and math and theory that we've learned over the last 50 years of computation, okay, but I don't think it's dismissible anymore. Okay, it's not nuclear fusion. You know, nuclear fusion is always 10 years away. Okay, quantum computing's here. It's young, it has limits, but it's beginning to show results. We're tackling engineering problems, and we're solving real problems using quantum computing. Do I have any questions?
You have very good experience with the real data and your problem is a quantum. Can you share a couple of the really exciting?
Yeah. So it's the great thing and the awful thing about quantum computing is how do we translate this problem into a quantum circuit? Okay, usually whenever I'm not able to translate a problem into a quantum circuit, I don't say that this is a bad idea or a bad solution. It's like I haven't figured out a good way to encode all this information. I've started some preliminary tests. I have my graph embedding methodology. Right now, that's just the raw graph. Okay, it's like you have these nodes in this structure. So I've started tests with data re-uploading to make this apply to chemoinformatics type data sets like MUTAG and things like this, where hey, I'm encoding atoms. I'm encoding the relational strength between these atoms and things like that. Okay, and so this has a potential to give me a compact, quick to compute, permutation invariant representation of this that I can then use for downstream machine learning. Whether that's simple kernel methods or a more advanced deep neural network. But like, it's those representation spaces, there's a lot, really clever people coming up with really clever ways to solve these problems. People are solving really interesting things in chemistry with things like sample-based quantum diagonalization. So if you're going to diagonalize a matrix, it's a very expensive operation. They're able to use quantum, the sample-based quantum diagonalization, where they're heuristically solving this, but using quantum for the difficult to calculate portions of it. And that's offering huge benefits. If you've ever dove deeply into like the machine learning aspects and how it works and stuff, machine learning becomes very, very trivial. You can compute the Hessian or diagonalize the matrix. Okay, a lot of the math is really, really easy, really, really fast. But like, that's a big if. But quantum is starting to offer insights into how we could at least heuristically solve those problems.
Yeah, from a where we are technology space. I'm just hearing this and I'm thinking punch cards, ENIAC, there was a famous person who said, I think that there's a market in the world for maybe 4 or 5 computers. Right. And he was right at the time with the capability of the systems, because this room couldn't fit the computer and the cooling space that you needed to handle that. And we're seeing the same thing with cloud quantum computing, right? So
yeah, here's the thing. I bet no amount of money to make prediction on what quantum computing looks like in 10 years. I put a significant bet on quantum computing still around in 10 years doing interesting things. Now it's one of those things, it's going to follow a slightly different trajectory than classical computers. This is only for solving these really difficult problems. Okay. Honestly, some major universities, government organizations, and corporations dedicated to quantum computing projects are going to have the quantum computers. Okay, I submit real problems on real hardware all the time as an API call. It doesn't make sense for someone who's not specialized in quantum computing to try to invest in that infrastructure. Whenever, we can offload this to IBM, whenever we go beyond our 10 minutes or whatever, they take our money and say, thank you very much. Okay, but, yeah.
Going back to the IBM Madonna.
Yeah.
For the last slide, your questions. This is real stereo large stereo RNA as well. I don't know how she knows.
I believe they got up to 82 bits for the representation. Yes.
It's an IBM, right?
Yes.
Why is Trump off ion factor? Is IBM super hard?
Oh, I'm sorry. These are different examples of that were not just on toy problems. So IBM Moderna is just the first one. Okay. Certified randomness on
this being different. Okay.
Yes.
And that's still about this, So they're really useful for designing, let's say, RNA molecules.
Yeah.
Like real scale.
It's kind of. So it's kind of in the fact of that we would like larger, but this is at the limits of classical computation as well. It's been about a year since I've read the paper, and this isn't my primary field. But this is a real class of problem. Going beyond, 80 elements is difficult with classical computation as well, especially whenever we talk about in the 3D space. A lot of people play with, look, we're holding this accuracy in a squashed planar representation, but that's not how folding really works. And so this applies to 3-dimensional higher order folding these RNA molecules. And so it's, so I'm not saying that this is outperforming all possible classical algorithms, but I'm saying it's at a competitive scale.
Another question related to, because mostly I look at automation.
Yeah.
But I think it raises very good point about the graph representation using quantum. I don't know that area, but still area.
Yeah.
So do you think if we have optimization problem, which have many nodes, many arcs, actually, right, we should use quantum-based representation first? Before we do the variational, using the typical variational quantum.
Yeah. So it's kind of a mixed problem.
Yeah.
Given an infinite quantum computer, absolutely. Okay, but like, well, I have access to 157 qubits. There's a depth limit what I can do. Now, here's the thing, if I can devise a representation of my problem that I think I can solve with a quantum circuit on current hardware, absolutely. I think that's a
So
solid.
when you represent whatever graph, right? So
Yeah.
you search, what do you do there? You still minimize or optimize some path, or
Yeah, so,
search, you do search.
yeah, so, my recent work was on an embedding. All right, it's purely deterministic, training free. And that's like a strength of it that like, hey, this creates a provably complete, by that I mean it is invariant to node ordering, it's injective, this graph always makes this output always represents this graph. Aspect of the quantum circuit. But it's one of those things where a lot of times it's a very clean mapping from a qubit is a node, and an entanglement is an edge.
Yeah.
Let's take a student's question.
Oh, yes, this.
Go ahead, yeah, you have a question.
Well, so I was just wondering, like, the problems that quantum computing would resolve and how they would like scale. Because one thing I was finding is that, quantum computing consumes like far more energy than conventional computing, right? And so, like, I could sort of see that becoming a problem if we start using quantum computing to solve, a vast amount of issues, like maybe in the far off future, haven't solved the problem of it consuming so much more energy. I feel like that could, add a significant burden on, how much energy we're producing.
Yeah,
So,
I agree with you, just like with some caveats. I completely agree that we need to be thoughtful and responsible about what we use resources for, whether it's quantum computing resources, whether that's electricity. We do need to be thoughtful and responsible with that. Okay, but it's, I don't know if anyone's ever heard the argument that like, oh, your electric car, you plug into the wall that comes from the power plant and is burning coal, like bypasses the efficiency argument there. So if quantum computing can give us a solution that meets a few different objectives, it makes sense to use it. Okay, does it give us a better solution? Okay, we have to weigh the cost of that better solution versus the cost of not having it. Okay, then there's the fact of like, okay, it uses more energy. Does it use more energy? Because like there's some of these problems that a classical high performance computing setup could run for days or weeks on. So it's like, yes, it's using more energy than my laptop. Okay, but it's actually using more energy overall. So it's one of those things where, and I'm not saying the answer to this is always like, oh, quantum computer's better. But like, we need to balance these resources versus the outputs that we're getting and things like that.
If I remember right, I think AI systems were used to develop a better tokamak reactor. So it's pushing the capabilities of fusion reactors. Simply built the architecture of the reactor was designed by the AI systems.
Yeah.
So one could lead to the other, which could.
Yes, no question.
Compared to, so which type of graphs work best, like, I should say, with quantum computing, which type of graphs benefit? Compared to classical?
It's more about what kind of problems. Okay, it's more about the kinds of problems that you're trying to solve. Okay, and that's just because you have a graph doesn't mean you're dealing with this like factorial search space. But if you're talking about like enumerating paths through that, trying to find the most efficient routing for your delivery company, stuff like that, it's whenever you're starting running into these walls where you're like, I am doing a poor job searching the space with classical computing alone. I'm getting these rough heuristic answers, and I understand that I'm making best guesses and I'm doing guess check here. Okay, then it's like, can we do a better job searching that space on computers? So it's like not so much what's the best graphs, what's the best problems. Now, at the same time, just with the nuts and bolts of how writing a quantum circuit works, you're going to have a hard time encoding 30 node features. Okay, like that's going to be a lot of computation just to get your graph put on a quantum computer before you do anything with it. So,
I want to ask you another question because of time. Most students from the computer science here, right? So they are looking for some future job and why they think quantum or AI plus quantum can give us more opportunity than traditional job because most students maybe are good for the programming and problem solving.
Yeah.
It's some traditional computing, right? And then AI is the additional aspect they actually building up.
Yeah.
But from the, we also look at a lot of internship opportunity through the quantum, and we're figuring out this is the really good career opportunity.
Yes.
Can you share that with them?
Yes.
Final.
And it's
If you have
going.
a further question, please stay here and talk.
Yeah, yeah. You know, and I think this is gonna have a kind of top-down propagation. Okay, I think it's gonna become a point in the future where like, oh, you're a serious AI researcher, you need some quant. Okay, I think there's gonna be a layer under that where it's a real differentiator for someone in a job market. But I wouldn't suspect that there didn't come a time where a passing familiarity with quantum algorithms wasn't seen as an initial interview question to a college student. I'm not saying that's 5 years from now. Okay, but in the same way that AI is propagated that same way. In 2003, you know, it was at the leading institutions, you know, neural networks, back propagation, you know, the Ivy Leagues and the big names and stuff like that. And it kind of filtered down to where like, okay, hey, you're a serious computational researcher, what do you know about AI? Okay, I have friends who started a career in what was data science, which was like a lot of data processing, you know, linear regression type stuff, some basic models and stuff, who, as they move on for another data science position, are now being asked about, you know, how do you incorporate, you know, LLM calls and kind of model would you use for this? So I foresee that same propagation style, where at some point, you know, it's going to be like you're going to have a passing familiarity with some quantum algorithms to be considered for a, you know, AI engineer or data science position.
But do you see that you have a more opportunity and then they may even apply for some?
Rapidly exploding. I've been working on this for 2 years. Every month there's more internships, there's more postings, there's more interest in quantum computing. It seems to be accelerating. Okay. I'll hang out for anybody who has questions.
Asking more question, it doesn't give you a question, and students from 5542, they have a sign up form here, make sure that they cannot,